So this is work with Laquan Wong at UC Irvine. And several people have provided data or technical help. And we'd like to thank Alan Nathan, Bart Smith, Clay Nunnally, Tom Tango, Lloyd Smith, and Bill Petty. And the data sets that we're using are from Savant and from Weather Underground. And I'll be talking about pitch movement, which depends on variables that the pitcher controls, depends on characteristics of the baseball, also depends on the environment. And if we're able to understand these dependencies, then that can help us with pitcher development, pitcher evaluation, pitch design, and help us with defining ball specifications that constrain trajectories to acceptable ranges, and help us optimize performance in different environments, and to monitor sensor systems. And something I'd like to point out from the beginning is that while physics constrains these models, the geometry of a baseball with its pattern of raised seams makes it impossible to model the aerodynamics from first principles. So data from sensors becomes very important in trying to build these models. And I'll be talking about data from both TrackMan and Hawkeye. And both systems measure the trajectory of a pitch and the spin vector magnitude, also known as the spin rate. And Hawkeye, in addition, gives us the direction of the spin vector, which is defined by the spin axis, and that is something that the pitcher controls. If we're using TrackMan, we can separate out three forces on a pitch. So if we have a pitch moving with a translational velocity v, then gravity pulls it down. We've got drag working opposite the velocity direction, and the Magnus force can cause the ball to change direction due to spin. Now, if we have Hawkeye, then we, as we said, additionally get the spin vector, and having the spin vector allows us to separate out the side force. And the side force is perpendicular to both the drag and the Magnus forces. And the side force is believed to be mostly due to this asymmetric flow separation that Bart talks about. Now, each one of these forces produces movement. So what we have here is a changeup, an average 20-20 changeup from the perspective of a right-handed pitcher. And we're showing the movement from 40 feet, and this circle has a radius of 12 inches. So you can see the contributions of the drag, the Magnus, and the side force to the movement. Now, the pitcher can control the magnitude and the direction of each one of these vectors. But there are some constraints. So for example, we're going to see that if a pitcher wants more side force, he has to sacrifice some Magnus force. The question then is, how can a pitcher use these forces to get the best performance on his pitches? And a tool that we can use to address this is the intrinsic pitch value. And what we're looking at here is for the parameters of the Pablo Lopez changeup in 2020. And we're plotting movement. And what this map tells us is the run value of the pitch as a function of the movement. And the way this works is that the positive numbers are good for the batter, and the negative numbers are good for the pitcher. So 0 is a league average pitch. And if we look at this pitch, and we look at the first vector, that takes us around close to the middle of the plot. And this is what he gets on his changeup with just the drag and the Magnus forces. And at this point, this is a little bit worse than an average major league pitch. But Pablo gets a lot of side force on his changeup, and that brings the pitch down here, and this becomes an elite changeup due to the side force that we get from the seam shifted wake. And you can see if he added more Magnus instead of the side force, more Magnus would just take the pitch up in this direction. You can see that that doesn't help. So for this pitch, the side force is very important to the performance of the pitch. So I'm going to talk about the Magnus and the side forces and how the pitchers can use these to try and control the shape of the pitch, try and optimize results. And here we've got the magnitude of the Magnus force. Depends on things like rho is the air density, CL is the lift coefficient. The lift coefficient depends on the spin parameter, which is the ratio of the spin rate to the velocity, also depends on the spin efficiency. So that's the magnitude, and then the direction of the Magnus force is in the direction of the cross product of the spin vector and the velocity. Now, it's easier to understand the spin efficiency if we break the spin vector up into components. So here we're taking the spin vector, this omega, and we can write it as a part that is parallel to the velocity. That's called the gyrospin, and a part that is perpendicular to the velocity. That's the transverse spin, also sometimes called the active spin or the useful spin. And then the spin efficiency is this ratio of the magnitude of the transverse spin to the magnitude of the spin vector. And if we look at some examples, here we've got a fastball with just backspin. So the Magnus force is going to be straight up on this pitch. And you can see that the spin vector and the velocity are perpendicular. That gives us a spin efficiency of 1. And then at the other extreme, we have the gyro ball, also known as a backup slider or a cement mixer. And for the gyro ball, you can see that the spin axis is now parallel to the velocity. And that gives us a Magnus force and a spin efficiency of 0. But even though we can't get any Magnus force with a gyro ball, as we said before, the more gyro you have on a pitch, the more potential you have for side force. And we'll be talking about that. And most pitches are somewhere in between. Most pitches have a spin efficiency that's somewhere between 0 and 1. And it turns out also the side force depend on the air density, and the air density depends on some weather parameters and also on the altitude. And if you want to learn more about this, here's an article. This is what we're using. This is first author's Terry Bayhill. And we use this to associate an air density with every pitch over the last few years. So from 2017 through 2020, we've assigned an air density to each of its more than 2.4 million pitches. We find the closest weather station on Weather Underground, and we find the closest time to the pitch. And on average, we are within about 14 minutes and a little bit less than 2 kilometers of the actual time and location of the pitch. So we get pretty good estimates of the air density for these pitches. And just an example of what the air density does, this is plotting vertical movement against the air density for Germán Marquez, 4-seam fastball a couple years ago. And you see that the vertical movement increases with the air density, as the model would predict. A low air density, you could think of a warm day in Colorado, and a higher air density, you can think of, say, a cold night in Boston. We also see that there's a lot of scatter here, and we're going to talk some more about that. Now, given the air density that we've gotten and what we measure with the sensor, we can now compute the lift coefficient and the spin parameter for every pitch. And it turns out that the lift coefficient is bounded by an increasing function of the spin parameter, this function here, f of s. And we're going to see that f of s is useful for a lot of different applications. We're also going to see it takes a lot of data to try and estimate this function, and we don't quite have enough Hawkeye at this point. So we're going to use TrackMan to recover this function, TrackMan from 2017 to 2019. And there's a few challenges that we've had to address. This is a plot of CL versus S. Okay, each point on here is a pitch from Irvine Santana, a 4-seam fastball from a few years ago. And we see a few things. We see that there is quite a bit of scatter here among these pitches in CL and S. We also see that there's some pretty serious outliers within this scatter. And another thing we see is that if we consider the pitches separately for home and away, the home pitches at target field are in blue, we see that there's a significant park bias between the away games, and we get a bigger CL for the home games. And we can trace that to him getting a larger vertical movement on pitches at home, which leads to a larger value of the lift coefficient. So these are a few things. Some other things that we have to address are that there's a different amount of scatter for different pitch types from different pitchers. This is just an example of the distribution of the lift coefficient. The red curve is a Marco Estrada four-seam fastball, and these are just for away games to remove the effects as much as possible of any park bias. But we see we have a tight distribution here for this Estrada pitch, and then the black curve here is a Matt Boyd changeup, and we see that we've got a lot more scatter. We've got a wider distribution. Okay, another issue that we have to address is that with TrackMan, we don't know the spin efficiency of a pitch. So what we've done is we've brought in some optical measurements that we got from Alan Nathan from an experiment that he did, and then he also gave us some measurements from some other experiments. And these are very small samples, maybe 20 pitches per experiment. Okay, but the benefit is that they have a explicit measurement, or the spin efficiency is known to be 1. And then we combine those with millions of TrackMan measurements with the unknown spin efficiency. And we have an optimization method that we use to combine all this data and come up with this f of s function. The optimization is written here. If you want details on any of the things that I'm going to talk about, I'm going to put up references to the papers at the end. So you can go to those papers and get all of the technical details. But the result is that we get a new model for this bounding function f of s, and that's the blue curve that's shown here. The light blue points, these are TrackMan pitch groups. So these light blue points are robust estimates of CL and S for a pitcher, pitch type, year combination, again, over 2017 to 2019. And the scatter in the vertical direction is due to the unknown spin efficiency associated with these points. And then the black and the red points here are the optical measurements that we got from Alan. And you can see there's quite a bit of scatter in these optical measurements. The previous model for this function is the green curve here, and that green curve was derived from these optical measurements. But what you see is there's quite a bit of TrackMan. There's a lot of TrackMan pitch groups in between the green and the blue curves, and that gives us this new model. That shows the improved accuracy of this new model. And as I said, this is useful for a number of things. It's useful, for example, for computing the spin efficiency from TrackMan data. And I'll show you some other things that we've looked at. Here, what we did is we were taking the pitches with the largest ratio of CL to this function f of s. So these are the points at the top of the distribution. And we broke these down by year. And we see that the red points from 2017 have the highest lift. That means you're getting the most Magnus force. And then the 2018 points are next highest, and then the 2019 points are the lowest. And we separately fit our model to each year separately. And we found that there was a different scale factor that lined up as we would see the points here. It's highest for 2017 and smallest for 2019. And we're trying to figure out what caused that. And I remembered reading the home run report, and the home run report had said that there were different seam heights for the ball between the different seasons. So we went to Lloyd Smith because he'd made those measurements, and he sent us the seam heights that he'd measured in his lab for the different years. And we plotted the model that we got for each of the different seasons. And sure enough, the scaling of the model matched up really well, strong correlation with the seam height. And that's in the articles if you want to go look at that plot. But something that's probably even easier to understand is here we're plotting just the average movement of pitches for each of the 3 seasons against the average seam height. And you see that there's a very strong linear relationship between movement and seam height. So as the seam height gets bigger, the movement on pitches goes up. And this is something that Enos Saris wrote about in The Athletic. And we can see, if we look over here, that even for very small changes, here we're looking at a change of about 1/2 of a 1,000th of an inch, we're getting a discernible change in movement. So a very small change in seam height can lead to a change in movement. And between 2017 and 2019, we're getting almost an inch of additional movement average on all pitches. And another thing that we can use this F of S function for is for sensor monitoring. As we said, this CL over F of S should max out at 1, but with noise, it can be bigger than 1. And on the left, we've got the distribution of this ratio for one game at SunTrust Park. And you see that we do get some pitches above 1. The 2 sigma point is about 1.5. So we shouldn't see too many pitches above 1.5. So this is a fairly typical looking distribution on the left. And then the next game at SunTrust Park, same sensor, we get the distribution on the right. And now you see we're getting a lot of pitches bigger than 1.5. We're getting a lot of pitches bigger than 2. So you could very quickly, in real time, be computing these ratios and looking at this distribution and determine that there is some issue with the sensor in this particular game that we're showing on the right. So those are some of the things we can do with this F of S function. Okay, so that was the Magnus force. Now I want to talk about the side force. So we've got here the side force magnitude. Also depends on the air density and depends on the side force coefficient, the C sub S. And the side force coefficient, as we said, increases with the fraction of gyrospin on a pitch. And as we also mentioned, the direction of the side force is in a direction that's perpendicular to both the velocity and the Magnus force directions. And as we also said, Hawkeye lets us separate out the contributions of the side force. And if you want to see details on that, again, I'll put up the references at the end of the talk. And here, what we've got is we've got a plot of C sub S, the side force coefficient, with the cosine of alpha. Okay, alpha here is the angle between the velocity vector and the spin vector. So that is the fraction of gyrospin on a pitch. At the left end, we've got no gyrospin. And then at the right end of the plot here, we've got maximum gyrospin. And these, again, each point here is a pitch group. So each point is a pitcher and a pitch type combination for 2020. And the sinkers are in red, and the four seams are in green, and then everything else is in blue. And the pitches over here, this group of blue pitches with the most gyrospin, these are all sliders or cutters, which are mostly gyro, as you can see. And then the thing we notice that the sinkers tend to get more side force than the four seams. And we also see that these points are bounded by pretty close to linear functions. Okay, we'll get a better idea as we get more Hawkeye data, but clearly the side force that we can get is going up with the gyrospin, and it looks like the bound is close to linear. What that allows us to do then is we can define a side force efficiency as the fraction of the maximum possible side force we can get for a given cosine alpha. So we can have a side force efficiency that's similar to the spin efficiency that we have for the Magnus force. And this side force efficiency then is going to depend on the orientation of the seams during the pitch trajectory. So if we can get video of pitches, then we can determine that relationship between the orientation of the seams and this side force efficiency. Now here we've got the average movement by pitch type and force for 2020. So if we look at the side force, and these are in inches, we look at the side force, the sinker gets the most movement, and that's followed by the split and then the changeup. So that's the magnitude. And if we look at the direction, this is the same plot we had before, where we've got the movement from 40 feet, and this circle has a radius of 12 inches. So if we look at the change-up, we see that the side force gives us arm side movement and down. The curveball down here has very little side force. If we look at the cutter and the foreseam, they give us glove side for the side force. The sinker, as we said, gives us the most side force, and it's also arm side and down. The split looks a lot like the change-up, as you'd expect. And the slider, on average, has very little side force, as we see here. And here we've got a table of leaders. So these are the guys who had at least 4 inches of movement on the sinker in 2020 for the side force. And we see we've got Lance Lynn at the top of the list, and then a lot of the seam shifted weight guys. You see Kyle Hendricks and Jared Hughes and Brad Keller. And here's the leaders for the changeup. We've already talked about Pablo Lopez. And then right there with him is Phillips Valdez. And if you've seen him pitch, he's got a lot of movement, a lot of downward movement on the changeup. And he gets very good results on the changeup, even though he throws it about half the time. He talks about trying to emulate Pedro with his changeup. And here's the four-seam leaders. We've got Brad Keller, we see again. And the guy at the top, Tyler Rogers. This might look like a typo, this 6.52, but it's not. This pitch, other sources classify it as a sinker. If you look at Brooks Baseball, they've got this pitch as a sinker. So if you look at just the side force movement on the pitch, the side force movement fits in a lot better with the sinkers than it does with the four seams. And here's the leaders for the cutter. We see that John Lester is at the top of the list. And then for the other pitches, these are all the guys that get at least 3 inches on average. If you haven't seen Framber Valdez throw a curveball, I'd recommend you pull up a video of that. Okay, now movement is nice, but the thing that we really want to try and optimize is the performance of a pitch. And as we showed earlier, we can use the intrinsic pitch value for that. And I'm going to talk a little bit more about those. Okay, the thing that you might be familiar with is the observed pitch value. Those are what you see on fan graphs for pitch values. And those give us the change in run expectancy for a pitch using linear weights. But the issue with observed pitch values is that they depend on a lot of factors that are beyond the control of the pitcher, which tends to give these values a fairly low degree of repeatability. The intrinsic pitch values are based on quantifying value in terms of 7 parameters: the velocity, location, movement, count, and the platoon configuration. And they're invariant to all of those sources of variability. And we've shown that intrinsic pitch values have a higher reliability and predicted value than other measures, including the observed pitch values. And if you want to learn more, there's an article here you can go to. If you don't want to read an article, the Driveline guys have put together about a 20-minute video talking about intrinsic pitch values, so you can go watch their video. And this is just an example of the reliability of these intrinsic pitch values for one configuration. Others are similar. We're plotting here the Cronbach reliability, that's the alpha. The black curve is the intrinsic values, and then the red curve is the observed values, and then N is the number of pitches. So the point is that we're getting a much higher degree of reliability for these intrinsic pitch values. Now, as I've said, they quantify pitch value as a function of 7 parameters, and I can't make plots in 7 dimensions. So what we can do is we can take slices through the space and fix some variables and look at some other variables. So here we can look at fixing everything except location and look at pitch value as a function of location. Here we are fixing everything except velocity and horizontal location. So we can see the exact run value of every mile per hour of velocity. Okay, here we're fixing everything except vertical movement and horizontal location. So we can see the exact value of every additional inch of vertical movement. But for this side force, what we're interested in is how much value we get from the additional movement on the pitch from the side force. So we've got the different pitch types, and then this is the magnitude of the movement in inches, so we've already seen. And now in the third column, we're plotting the run value of the side force. So if we look at all the pitches thrown in 2020, what is the added run value of the side force? And this is per 100 pitches. Okay, so negative is good for the pitcher. Negative brings down the run, so negative is good for the pitcher. And the first thing you see is that all these numbers are negative, which means that on average, the side force is helping pitchers. And then if we look more carefully, we see that it helps per pitch. It helps the split the most, followed by the sinker and then the changeup. And it helps the curveball the least. We get very little benefit in performance from the side force for the curveball. So these are averages. And we can also look at some specific cases. Okay, this is Lance Lynn and his sinker. And this first vector here, we're looking again at intrinsic value as a function of movement. And the first vector is where he gets to with just the drag and the Magnus. And this is a very hittable pitch. You would not want to throw this pitch in the big leagues. And if you tried to, you wouldn't last very long. It's got, these are now in WOBA units over here, but the intrinsic values is not good with just the drag and the Magnus. But we remember that Lance Lynn got the most side force on his sinker of anybody. And if we add in the side force, that brings the pitch in the movement space down to here. And now it becomes an above average big league pitch. Now we can look at some other examples. This is Aaron Sivali and his sinker. And if we look at this pitch, we put in its parameters, we get the drag and Magnus putting it here. And unfortunately for him, when he adds the side force, he was one of our side force leaders, if you remember back from the table, but for him, the side force makes the pitch worse. So on average, side force helps, but there's some pitchers and pitches that the side force is going to hurt. All right, I'll give you one more so we can leave you with a happy thought here. This is Alec Mills. And his sinker, the drag plus Magnus, puts him here. That's a little bit worse than average big league pitch. But we add in the side force, and now it goes to an above average big league pitch. Okay, so in summary, we've got new models for the Magnus and the side forces, and we've got a number of applications that we've talked about. And if you want to read more, we've got the technical details at these reports. If you have questions, I can answer them here, or I'm sorry we can't be in the same place, but I'm happy to answer questions by email or get you any references that you might need. Email is ghealey@uci.edu. So that's it. Thank you.